All right, it's 11:15. We'll get started. So remember, this week you've got homework due on Friday, and you have PLAs to do. So don't forget about that stuff. And don't forget about the material that we're covering this week, because you're going to need it after spring break, because all this stuff is going to be on the Section 3 exam. So you can look up as to when that exam is going to be on the PDF syllabus. Make sure you take some good notes this week and put that in your memory bank, and then bring it out when we get back from spring break. So any questions or any comments? I've had some good office hours visits this week. I'll have office hours tomorrow to clean things up. If you need help on anything, let me know. You can make an appointment up to maybe 3 p.m. on Friday. So just let me know what help you need. Also, I have homework to do this week. I have to get your written exam parts graded, so I'll get that really going. There's still some that are left ungraded, but I'll get that. You should know exactly sort of where you stand in the class to date by the end of this week, including clickers, which I updated, and it looks like everyone's registered. Things are going well in clicker land, at least so far. All right, any questions, comments? Okay, so we're going to talk about copolymers today, and this is the hardest thing that's going to be on exam 3. So we're going to derive an equation. We don't derive many equations in this class. We use them, but this one is really interesting and important, and it's a little bit harder to solve than some of the other stuff that we've done before. But if you really pay attention to sort of how we set it up this class, review it, it'll make a lot of sense when we get to the calculation part. Okay, so we're going to talk about copolymers probably for 2 or 3 more days. And so the copolymers we're talking about in this section are really all going to be addition copolymers. So this is addition or chain growth. We can make step growth copolymers. Some people talk about things like bisphenol A polycarbonate as a copolymer of bisphenol A and phosgene. That's fine. That's a perfectly alternating copolymer, but we really don't describe step growth polymers the same way as we're going to describe these chain growth copolymers. And so that's something to keep thinking about, and it'll be obvious once we start to discuss the chemistry. So the type of copolymers we're going to focus on are usually copolymers where there is no real pattern to the sequence. Now, in some cases, we can have perfectly alternating copolymers, and we'll call those perfectly alternating. That's a very special case of cross propagation that we'll talk about. Most of the time we'll talk about statistical copolymers, which are sort of no pattern to the monomers. The monomer incorporation is just based on the statistics of the monomers that you put in. That's where statistical copolymers come from. And it turns out that random copolymers have an exact definition in this context. And so I'll show you exactly what a random copolymer means by definition when we get to it. We're going to talk a little bit about blockiness in copolymers, and blockiness means few of B. Let me get that looking right. Or let's say, few of B, maybe more. A couple of B, many of B, followed by mostly A. And so when I refer to a blocky type copolymer, it means we've got a run of B, followed by a run of A, probably maybe by another run of B, and another run of A. Officially, that's called a segmented copolymer, but let's not talk about that right now. It's just a blocky type copolymer. If you want to make a diblock, so a special case of this is a diblock copolymer where you have like 2,000 molecular weight of A followed by 2,000 molecular weight of B. That's usually made using anionic living polymerization because you control exactly that type of diblock chemistry. And so we'll get into the details as we get there. We're not going to talk about graph copolymers in this class, but this gives you sort of a framework to think about copolymers. And we want to describe the situation where we have this. So we have a mixture of monomers, in this case, orange colored monomers and blue colored monomers. So remember, the way we make a polymer, we dump all our monomers and solvent in, then we're going to initiate it somehow because this is a chain growth addition polymerization. And then we're going to let the monomers incorporate into the chain in order to get these certain sequences. So you can see orange monomer reacting with orange monomer here. You can see orange monomer reacting with blue monomer here. Blue monomer reacting with orange monomer here. And orange monomer somewhere, and blue monomer is going to react with blue monomer. And so this depends on the chemistry of the active center and the chemistry of the monomers. And we're going to describe those things quantitatively. Did I see a hand up? Yes.
Yeah, just have a question about the blockiness.
Yeah.
So can you have skew A followed by B?
Yes. So you can have lots of different situations of blockiness. It will be sort of quantitatively obvious what's happening when we have blockiness versus if we have just a statistical or random copolymer or some of these other cases. But you do want to be familiar with this concept of blockiness where you have significant runs of one versus the other. Sometimes you have a bunch of B, then you have 1A, then you have a bunch more B and maybe 1A and a bunch more B until you run out of B. Remember, we're consuming monomer, and so you might run out of one monomer and then you have no choice. Then you have to have A after that. That would be a blocky type copolymer. Okay. And again, we're talking about chain growth, and so we're talking about making high molecular weight polymer over all or a large range of monomer conversion. And so this is going to get confusing because we're going to talk about mole fractions of A versus mole fractions of B. We're going to talk about monomer conversion, and we're going to talk about molecular weight and composition of the polymer. So you really want to pay attention to what's the x-axis, what's the y-axis, and what are we talking about? Otherwise, you're going to be drawing plots and trying to remember those shapes and not really getting the right answer. So this is going to be important to pay attention to, especially when we get to the end of this lecture. All right, so this is a situation. We have two different active centers, and I'm going to switch from orange and blue to A and B. We have A active centers and B active centers, and the question is, what monomer are they going to add? Are they going to add A, or are they going to add B? So we've got these four reactions that we talked about, and we talked about homopropagation. Notice that the active center in homopropagation doesn't change. No change in active center. Whereas in cross propagation or heteropropagation, you have a change in the active center. So a B active center, which is where the star is, changes to an A active center. And vice versa, the A active center changes to a B in heteropropagation. And we have these rate constants. So pay attention to these because these will be important as we start to dig into what we call the reactivity ratio or the preference of an active center to add one monomer versus the other. And we're going to have lots of A and B's flying around. And so you want to have a little piece of scratch paper to remember this setup. So these rate constants, K is always a lowercase k is always a rate constant in this class, mostly, are named for the active center first, followed by the monomer it's going to add. So it's K, A, B. First letter is active center. Next letter is monomer to add. So KAA is active center A, adding an A monomer. KBB is active center B, adding a B monomer. And same thing, KBA, B active center reacting with A monomer. And then KAB is A active center reacting with B monomer. Those last two get confusing, and so we have to keep that straight because we have a rate constant for active center A, or we have two rate constants for active center A, right? So those are the two reactions, 1 and 4, where A active center is reacting with either monomer A or monomer B. So we have two rate constants to describe what the active center A can do. Same thing with active center B. If you look at equations 2 and 3, active center B can react with B, or active center B can react with monomer A. Now, again, there's a lot of A's and B's flying around, but there's only 4 reactions. And we're only going to cover a mixture of 2 monomers. Remember the physical situation, a mixture of 2 monomers making a polymer. What is the composition of that polymer? And we're going to relate what's up here, or our monomer mixture, to what winds up in the polymer by analyzing these rate constants. All right. Any questions so far? All right. It will become obvious and more user-friendly the further we get in the lecture. So I don't intend to confuse all the way to the end. It's a little bit confusing now, and it's going to get a lot easier once we get to the punchline here. Okay, where is A consumed? This is not A star, this is monomer A. So you're going to have to be really on top of, are we talking about the active center, which will be denoted with the star, or are we talking about the monomers? So consumption of A, we consume monomer in reaction 1 and reaction 3. That's it. Otherwise, we're consuming B monomer. And so we can write down a rate expression for that. Remember, the rate of polymerization is defined by the rate of disappearance of the monomer versus time. So you've seen this definition before. As the monomer concentration is going down, we can define that rate. And so we have a rate constant KAA. This is for reaction 1. And we multiply it times the concentration of the reactants, right? This is just generic rate expression, KAA times active center, concentration of active center A times concentration of A. We've done that before. You've done that for lots of things. You can just write that down. Although A also is decreased, monomer A is also decreased in reaction 3. So we need a rate expression for that. So we take the rate constant, KBA, times the concentration of active center B, times the concentration of monomer A. So we haven't done anything fancy here. The hard part was figuring out what these 4 equations were and getting the rate constants. But now that we have all of the reactants and we have all the rate constants, you can write the rate expression. Who's confused on this? Okay, this is the same definition for rate of polymerization that we've used before. We just have some other reactions to think about. Same thing for B. So again, you want to get the reactions correct and the rate constants correct. And so just don't start writing down A's and B's and hope for the best. Write down the reactions, analyze the rate constants, analyze the concentration of reactants, and you can't get it wrong. Okay. So we have those things. Oh, I'm pointing at the wrong thing. So we have our rate of monomer A consumption, or rate of polymerization of A, rate of polymerization of B. And so now, in order to figure out, we know those individual rates, right? We need to know the relative rates, because what's happening is you're having A and B monomers out there in solution. But in order to make a polymer out of those, you need to know the relative incorporation of A and B, because that gives you the composition of this polymer, right? And so it's not only sufficient to know how many orange monomers and how many blue monomers you start with. You could have 90% orange monomers and 10% blue monomers, or you could have 50% orange monomers and 50% blue monomers, right? We get to control that. We get to put in whatever monomer mixture we think, and it doesn't always have to be equimolar. It can be 50-50, it could be 90-10, 85-15, whatever. Of course, the mole fraction the mole fraction has to add up to 1, or our percentage has to add up to 1. But it's the rate, these rate constants, if orange incorporates faster than blue, it means that whatever's happening with the orange monomer, it's reacting into the chain first. And that's what gives us more orange versus more blue. So the composition of the polymer is a function of the starting monomer mixture and these rate constants. And we're going to have an easy way to track that. And so the polymer, we'd really like to know, this gives us an idea of the relative incorporation of the two monomers into the polymer, the rate of disappearance of monomer A over the rate of disappearance of monomer B, and we get this big thing right here. So we actually know a lot of these variables, right? We know the monomer concentrations. You guys have calculated monomer concentrations in the last unit, you know, either given the monomer density or some other metric. We can figure out what rate constants of reactions are. There's tables for that, and we're actually going to look up the ratio of rate constants. So I'll show you how to do that in a second. And the hard part about this, just like before, is that we don't, or we're not often given M dot, right? Or concentration of B star or A star. So if you remember last unit, we had M dot equals a bunch of other things, and we had to solve for that in order to get the rate of polymerization. It's a very similar story here, that we have to come up with an expression for the concentration of A star and concentration of B star. So the question is, how did we do that last time? We wrote down rate of polymerization is M dot Kp times concentration of M. How did we solve for M dot? Do you remember what assumption we made? It's a vocab word. It was on your study list. Yes. The steady state approximation. And let's review what the steady state approximation was. What do we do when we make the steady state approximation? We set what equal to what? Yes.
The radicals being terminated equal the radicals being initiated.
That's right. We said that the rate of initiation equals the rate of termination, which gives us a steady state concentration of active centers, or of radicals if we're talking about free radical polymerization. So that's right. We made that steady state approximation, and that means that these concentrations are constant. And so we're going to do exactly the same thing in a second. So this is a clicker question. You can get out your clickers. We're in CD. All right. So the active center concentration. What reactions contribute to a change in active center A and active center B? So we have our key reactions. You should just print this slide out so you remember what those key reactions are and all the rate constants. We have our rate expressions right here for the rate of polymerization. And so we'd really like to know which reactions change the active centers. 45, looks like there's a little bit, oh, there we go. All right, above 50, we're doing well. Awesome. Okay, so if we look at the reactions, let's see. We have a B active center, reacts with B, gives you a B active center, not this one. A active center reacts with A monomer, gives you an A active center, not that one either. So it's equations 3 and 4, where you have the change of the active center. So you go from B active center reacting with A or B, and if it picks A, or if it happens to be a reaction with A, you change the active center now to an A active center. Yes?
Now, why is the equations we use to find the concentration of the actual stars different from the ones we found earlier?
Oh yeah, sorry. This is for, I misspoke. This is for the rate of polymerization or the rate of monomer consumption. This is for the change in active center, right? Yeah, sorry about that. I didn't go through that. But you sort of get it, right? You know, nothing much happens with the active center, or nothing happens with the active center concentration in homopropagation. It's the cross propagation where now you have a different active center. Okay, so we make the steady state approximation. And so we say that the change in active center A and the change in active center B equals 0. That's what the steady state approximation is. It's not that the concentration is 0. So we need concentration of A star to be finite because that's going to be making polymer for us. Same with B star. And so it's the change of concentration that's 0. That means steady state. And if we solve all this and rearrange, what we get, and this is really interesting, the ratio of A star to B star, we can express in terms of the reaction rate constants and their concentrations. And we know both of those things, right? We can measure Ks or we can look them up. And of course, we get to choose concentration. So we know everything on the right-hand side of this equation, and we can figure out what the ratio is. Now, you'll have to excuse my hand waviness. If you take this expression and substitute it into this thing, just trust me on this, it'll work out. You get this. And so now we have an expression for the relative ratio of the concentrate, or the change in the relative ratio of the concentration A and B in terms of variables that we know. So we're going to denote RA as KAA over KAB. So KAA there over KAB there. So what is RA? Let me write it down for you. KAA over KAB. What does RA tell you about those two reactions? What if KAA is really fast and KAB is really slow? That's what the rate constants are. It tells you about the kinetics of the reaction. What if KAA is fast and KAB is slow? What does that tell you? Yes. Exactly. It's more likely. So a fast reaction is more likely to happen. So a high RA tells you that A wants to add A, and A doesn't necessarily want to add B, unless it has no choice. If there's only B monomer around and there's no A monomer around, an A active center has no choice but to react with B. And we'll talk about that. That's where things get confusing because the copolymer incorporation or the copolymer composition is a function of both the rate constants and the concentration of two monomers, what's available. You have to remember that. Okay, same thing with RB equals KBB over KBA. Notice that the subscript of this R, and the R stands for reactivity ratio in this unit, RB is talking about what's happening with the B active center. So this is B active center reacting with B. This is B active center reacting with A. And so if RB is high, reaction 2 is favored over reaction 3. And so, like I said, we have a lot of A's and B's flying around here. We're going to have RAs, RBs, these rate constants. It all stems back to this fundamental set of reactions and what's happening with the active centers. What does it mean when RA is high? What does it mean when RB is high? What does it mean when RA is low? What does it mean when RB is low? What if RB equals 1? What do you know when RB is 1? Yes.
They have equal reaction rates.
They have equal reaction rates. Doesn't mean that the copolymer is going to be equal, because it depends on what monomers are around, right? What monomers are available. But when you have equal reaction rates, that's a special case. We'll talk about that. All right. So we just talked about reactivity ratios. Yeah. These are R equals reactivity. RA, RB. This is different than stoichiometric offset. It will be completely obvious when we're talking about stoichiometric offset and Carruthers versus reactivity ratios. But these reactivity ratios have been studied in depth because a lot of the industrial polymers that we use are copolymers. And so people would really like to know what monomers to put into the reaction in order to get the target copolymer of interest. Okay, yeah, don't confuse with reactant ratio. All right, another clicker question. I think we're at 55 last time. That's excellent. So if RA is greater than 1, what does it mean? A nice part is that you remember what the definition of the reactivity ratio is. Remember, the letter here is the first subscript because we're talking about active center A star and what it's going to do. Is it going to add monomer A or is it going to add monomer B? We go back to our fundamental set of equations and so say, okay, you know, here's KAA, here's KAB. Okay, if it's greater than 1, we got most everyone. A prefers to add A. It's that simple if you are able to have really good bookkeeping for which reactions, what's happening when, don't get A and B reversed. It's a bookkeeping exercise. And I'll tell you that most reactivity ratios are named for the first letter of the monomer. And so it's more like R styrene methacrylate, RSM, or something like that. So when you look up in a table and you don't see RAB, you see some other nomenclature, you just have to look very carefully to figure out which monomer they're talking about or which monomer pair they're talking about. They're done a few different ways, but it will be obvious from the table what's happening. All right, any questions so far? Any comments so far? Okay. So the reactivity ratios, which we're going to use extensively, go back to the 4 equations, homo and hetero propagation that we've talked about, and they're the ratio of the coefficients for these 2 reactions, or the likeliness or the speed of those 2 reactions. And so we just need to figure out what's going on with the concentrations, and then we're all set to plug it into the equation. All right, and so we have this equation. So the change in monomer A versus the change in monomer B is going to tell us what monomers from solution go into the copolymer. We know what reactivity ratios are now, and we just need information on the concentrations. Sometimes that's given. I'll tell you what the concentration of A is. I'll tell you what the concentration of B is. But more often, we're interested in the mole fraction. And so if we define small fa as the mole fraction of A, we can define mole fraction of B as 1 minus FA, right? So mole fraction is just concentration of what we're interested in over total concentration, because all the per liters cancel out. So you get moles over moles. And so we're only talking about 2 monomers. And so once we define FA, 1 minus FA is FB. So if you don't believe me that this is mole fraction, just put in moles per liter, moles per liter, moles per liter, right? All the liters cancel out and you have moles over moles. You're all set. Okay. Capital FA now is the mole fraction in the polymer. And we know that this is describing the change of concentration of monomers in solution. And so if we track those changes, we know what's going into the polymer, right? Because either the monomer has to be in solution or it has to be in the polymer. So we can define the mole fraction of A in the polymer as that, and the mole fraction of B in the polymer is this. So this is monomers in solution, as I'll often describe it, or in the reaction mixture. And since polymers are awesome, they get a capital letter. This class is all about polymers, capital, and so it's easy to remember. Capital letter is polymer. That's the only way I can remember it. All right. So we have some definitions, we have some variables. You can look at the derivation in the book. So if you don't believe this derivation, read the book, study it. But I'll tell you that learning how to interpret these and then learning to use these two equations, which are called the copolymer equations, is really what I'm going to hold you to in this class. So you want to know about the steady state approximation. You want to know about the 4 fundamental reactions and what's going on and why the reactivity ratios are what they are. But all the derivations and solving for things lead you to this result, which is what we're going to use. Because if you look at these equations, you've got reactivity ratios. We can look those up. We've got mole fractions. We can figure those out just like we can figure out concentrations. And so we could get the composition of the polymer from RA, RB, and monomer mole fractions. So just to look back at this diagram once more, because this is a situation that we're interested in, by knowing the reactivity ratios for these 2 monomers and knowing the mole fraction of the monomers at a given point in time, we can get the composition of the polymer. And that's exactly what we want. So we've taken this picture and reduced it down to, well, we've reduced it down to these copolymer equations and things that we can look up or figure out. And so these are the equations that we use then to design copolymers, or to figure out what the copolymer composition is for a given situation. And we're going to practice this. We're going to practice this a lot. We're going to practice it in the next homework after spring break. I'm going to remind you about this equation on Monday after spring break because you'll use it a lot. Okay. And so the question is, what can we do with these equations? Now, these are easy equations to solve. I suggest you break out your Excel notebook, or if you program in Python or MATLAB or whatever, it's fine. You can put these right in there. But being able to enter these accurately in Excel is going to be key to your happiness on the homework. And so I will go through some of that, and you can try it out on these examples here to make sure that your sheet is working. Any questions or comments so far? All right. Clicker question. and I will walk you through this, but I want to see who is paying attention. So you have an equimolar mixture of A and B monomers. What does that tell you right away? Equimolar mixture. Yes. Equal composition, that's right. What does that tell you about the variables that you need to know in these equations? What are the mole fractions of A and B if we're in an equimolar mixture? Yes, Fa equals 0.5 and Fb equals 0.5. That is not moles per liter. That is not Fa equals 1 and Fb equals 1 because the mole fractions have to sum to 1. So don't forget about mole fractions and all that other stuff. We're not talking concentrations either. We actually don't know what the concentration is when the mole fraction is 0.5 and 0.5. We just know that the mole fractions are equal or the concentrations are equal. It could be high concentration, they can be low concentration. We don't know. But that's key in order to go from the words to what the variables are. And I'm going to expect that you know that. So when you see equimolar, you'll know exactly what that means and you won't get that wrong. Or if I give you concentrations, you can calculate mole fractions, right? Because it's not hard to calculate mole fractions from the concentrations. I expect you to be able to do that. All right. So we've got Fa and Fb. The only two other variables that we need to know are Ra and Rb. And I gave those right to you, right there. So the magic for this problem is just trying to plug and chug it accurately. And like I said, on the homework or in your independent studying, you should definitely make an Excel sheet or a little program to spit out the sort of plots I'm going to show you. You are not going to have access to Excel or your Python sheet during the exam. And so you will have to plug and chug this once or twice, but it's not going to be 10 questions on plug and chugging the copolymer equations. But you will have to interpret it. You'll have to be able to enter it accurately. Make sure you're able to do it both ways. Okay, so if we plug everything in, what is the composition of the copolymer formed at low monomer conversions? So there's a couple key words here. Low monomer conversion means Fa and Fb don't change, or the concentrations of those monomers don't change. So we start with an equimolar mixture. We run a very small conversion, like 5%, and then we see what the copolymer composition is. And we're trying to solve for Fa and Fb. Do we have to solve for both of them? Do we have to plug and chug both Fa and Fb? Why not? There's only, go ahead. Oh, there's only two monomers, right? And so if we solve for Fa, Fb is 1 minus Fa. So we get Fb for free when we solve for Fa, and vice versa. And so you really want to be sure that you're using whichever copolymer equation you're using, and you're answering the question I ask you in terms of whether I'm asking you for A or B. That's really important, right? Fb equals 1 minus Fa in a binary system. Don't forget about that. Okay, so equimolar, Fa and Fb is 0.5. We substitute in all the reactivity ratios, and we just get straight up Fa is 0.46. So what does that mean? That means that the mole fraction of A is 0.46, or it's 46 mole percent. A, and the rest is B. So what's the mole fraction of B? Not a trick question. Go ahead.
54%.
Has to be 54% or 0.54. So it doesn't matter if you solve for Fa or Fb, but you have to answer the question in the way that I'm asking it, right? Because if you do it the wrong way, you'll be telling me about the wrong monomer. So that's the crux of a lot of these problems. You'll get a setup like this. You may have to go look for the reactivity ratios. I might ask you about something else in terms of monomer incorporation. You know, these reactivity ratios, one being above 1 and one being below 1 is something you want to keep an eye out for. So you could say, what about RB? So if RB is greater than 1, what does that mean? Yes.
B on B interaction with favor.
That's right. So you're going to favor B active center reacting with B monomer. What does RA of less than 1 mean? A active center prefers to add what? B. So if B active center prefers to add B and A active center prefers to add B, what's going to wind up in the polymer more of? B. And that's exactly what we calculated right here. So we get OFB equals 0.54, and we say that polymer is enriched in B. The polymer is enriched in B. And that's really cool. We started with 50-50, A and B, and the native reactivity of those active centers or the rate constants, can't control those. We could just measure them and look them up. We got a copolymer that's not 50-50. We got a copolymer that's enriched in B, and it follows our Spidey sense for what these reactivity ratios mean. Okay, RB means what's happening with the B active center. Wants to add B because RB is greater than 1. RA, what's happening with the A active center? Oh, the A active center actually wants to add B too. And if that's the case, if they both prefer to add B, there's going to be more B in the copolymer than what's in the monomer mixture on a relative basis. That is a big concept, and that's going to take a little bit of thinking in order to square that up. So I suggest you study that and think about it. Any questions or comments? All right, a few more slides. We're getting to the crux of how to think about this. So if we take the previous problem and we put it in Excel and we start to calculate for all values of FA. So this is monomer, A monomer, mole fraction. And remember, mole fractions can go from 0 to 1. So an FA of 1 means all A. And so this plot better end up at 1, 1, right? So if you have all monomer A, you're going to get all monomer A in the copolymer. If you have no monomer A, you're going to have no monomer A in the copolymer. So it has to go from the origin up to 1, 1. So that's a good check to make sure your Excel sheet is working. And then what I did here was I took 0.5 molar steps for FA as my x-axis. Whoops. We get to pick FA, right? I get to mix whatever monomers I want to into my reaction mixture. And so for every possible FA, and I don't need to go at smaller steps, right? This gives me a pretty smooth curve. I can interpolate this if I want. So for every FA, I have these reactivity ratios. I don't get to pick these. I just look those up. I can calculate FB, right? Once I know FA, FB is a piece of cake. And then I can calculate my copolymer composition. And this is going to be y-axis. Right here, polymer. Because polymers are awesome, and so they get capital letters. All right. And so when I plug in 0.5, I go up here. I started with monomer FA of 0.5, I go up and read this right off of the plot. And then, whoops, that's not quite 0.46, and that's not quite a straight line. There we go. In the polymer, I've got 0.46, and that's how I interpret this. So I could have asked I could have said the question, well, I have 90%, 90 mole percent Fa, 10 mole percent Fb in my monomer mixture. And I get this copolymer composition. So I'm not going to ask you to generate this curve on the exam. I'm going to ask you to interpret the curve. So you're going to see a few of these. You're going to have to tell me what's going on with this curve. But this curve is generated exactly the same as this one point. It's just for all different compositions. And so again, you need to look at the X and Y axis, think about what I'm saying, and then how does that square up with what's happening with the polymer? And usually I will always have small Fa versus big Fa. So I won't put small Fa versus big Fb. That would be confusing, although you should be able to deal with that. But mostly I'm going to talk about what's in the monomer mixture and then what happens to that same monomer in the polymer. And so here's our last clicker question of the day. What if I have a plot like this? So this is Fa, exactly the same axes as I showed you before. Here's Fa here. And if I put in 0.5 Fa, wow, I'm getting a lot of A in the polymer. So right away from this plot, if I even put in a little bit of monomer A, I'm still getting an awful lot of A in the polymer. So polymer is enriched. What monomer is enriched in this polymer? A. So what does that mean for our reactivity ratios? If I'm enriched in A, that means this reaction is really fast. I'm adding A. And it means that this reaction is really fast. I'm still adding A. So what does that mean for our reactivity ratios? If the numerator of one is high and the denominator of the other is high, what is the likely situation? Oh, awesome. I got 55 already. Great. So what that means is RA is larger than RB. So if the numerator in RA is high and the denominator in RB is high, it's probably that RA is greater than RB. Don't put your stuff away. We still have one more slide to go. Okay, study that, think about it, and it gets more complicated because this is the figure that you're going to have to interpret. And I don't love this figure. It came from the book. The book's not in color. You should go home and make this figure in Excel so you can see what's going on. But you see all these really interesting lines. So the solid line when RA equals RB is right here. Boom. That is the definition of a random copolymer, as you'll figure out. And so when RA is 1 and RB is 1, what does that mean? Yes?
They're just as likely to react to each other.
All reactions have equal likelihood, or all reactions have same rate constants, at least for homopropagation versus heteropropagation. So it's not all 4 reactions. It's KAA, KAB are equal, and then same thing for B, KBB, KBA. That's the definition of a random copolymer, and that's the 45-degree line on that plot. You have to look very closely at some of these, like the spaced dashed line is right here. RB is really high. RA is pretty low. And so is the polymer enriched in A or B for this curve? Polymer is enriched in B. Okay, great. We've got enriched in A, enriched in B. What about a polymer that crosses over the 45-degree line? What is going on there? So that's the short dash line. I'll tell you that this one is this one right here. What if both the reactivity ratios below 1 or both reactivity ratios above 1? What does that mean? Yes.
I mean, that we figured at one point, but then changes.
That's right. So we'll talk about that. It means that the cross propagation, well, we just go back to the fundamental reactions. And if they're both, whoops, if they're both less than 1, it means that cross propagation is favored. If they're both greater than 1, it means that homopropagation is favored for both active centers. And we'll talk about how that matters because we're changing both the concentration and the reactivity ratio. We're changing this FA, and that changes the plot. Talk about that on Friday. Don't forget your homework and PLAs. See you next lecture.